Hi everyone, it's really an honor to be here today and especially to be following Alsulaiman, who is actually my PhD supervisor. So you're going to see a lot of themes that have been translated down to me. So a few things about myself. So I did my PhD and master's with Alsulaiman and did a postdoc at MIT. And just a year and a half ago, I started my research group at KAUST. So KAUST is over basically in Saudi Arabia, just an hour north of the city Jeddah, which was my hometown, but I'd never lived there because I'd studied abroad most of my life. But I'm really happy to be there now. If you're interested in snorkeling and diving, definitely come and visit us. All right, so today I'm going to be talking about basically the same topics that Alsulaiman talked about, but applied to cancer diagnostics using different materials and different strategies. So I'm going to be kind of going through very quickly with some of my introductory slides. So what we're going to develop is electrochemical biosensor for microRNA detection. In this case, we're going to be using a new material that we've developed, PNA conjugated vaccines. All right, so I'm going to go through this introductory slide very quickly. So what is the challenge that we're trying to address? And that's the burden of cancer, being late stage, inaccurate, or invasive. So if we look at, let's say, prostate cancer as an example, a patient has to first present clinical symptoms. This is already in the late stages of the disease. After that, a patient typically has a blood test. It's most likely a protein-based blood test, and that results in a lot of false positive results. And in the end, most patients still have to undergo an invasive surgery like a tissue biopsy to confirm the presence of a neoplasm. So this is the traditional and a very reactive approach in medicine. And of course, there's a major drive to go towards a much more proactive precision medicine-based approach that is minimally invasive using point-of-care devices, as Alsulaiman already talked about. And this is something that we're trying to do in our lab. So the idea is you take a liquid biopsy, blood or urine, and then apply it onto an advanced technology, a point-of-care device, and from there detect a number of biomarkers, whether that's DNA, RNA, proteins. And then the analysis from that is then used to inform clinical decisions, whether that's early diagnosis or choice of therapy. So this is the ultimate goal, and I'm going to talk about the approach that we're taking in order to develop that. Of course, my favorite biomarker is the biomarker that Alsulaiman introduced to me in my PhD, and that's microRNA. So basically, I don't need to go through too much about microRNA, but I'm going to talk about how it's dysregulated in cancer and how it's a very promising biomarker for cancer. So if you compare the levels of microRNA in healthy patients compared to cancer patients, you'll see that there's extreme dysregulation, either through overexpression or underexpression of microRNA in the healthy patients compared to the cancer patients. But the really cool thing is if you look at the dysregulation profile, it is actually disease specific. So it can tell you the type of disease, it can tell you the stage of the disease. It could also help inform which therapy or chemotherapy drug is going to work best. So of course, we're trying to detect that. This is an example of just a heat map for gastric cancer. You'll see everything red here is upregulation of a whole panel of microRNA. Some of them are downregulated. And so ideally, we want the readout of our biosensor or our technology to look something like this, giving us an expression profile, ideally as quantitative as possible, with as many microRNAs as possible. So as much multiplexing as we can do. Of course, right, so this is the other really cool thing that's already Alsulaiman mentioned. The microRNA ends up in the bloodstream. From the bloodstream, it ends up into all biological fluids, which is great. That means you can do minimally invasive detection. Of course, there are challenges, which Alsulaiman already mentioned, right? They're very low in concentrations, they're very short in length, and the sequence homology we already talked about. We also talked about the conventional strategies and why we want to move away from them. Also, I have an additional slide here showing you that, if I look at a conventional RT-PCR test kit, they're typically $100, right, that we all did during COVID. And most of the money, you'll see that actually, so 10% of the money goes to paying for the lab personnel, right, so the HR, and 87% goes into the reagents. And Alsulaiman already mentioned all of the different enzymes and the fluorescently labeled probes that are expensive, right? So we want to minimize both of these sources of cost, right? So our aim, match the sensitivity and specificity of PCR, right, ideally, but do it in a much simpler, robust manner. Ideally, we don't need any lab personnel to be there to operate these devices. No enzymes, and cost and time efficient way. So this is the approach that we're taking. We want to develop an electrochemical biosensor for microRNA, same exact transduction mechanism as a glucose monitoring device. And you can already tell one of the advantages of that being very amenable for point of care. There are devices already being used all the time around this, taking advantage of this transduction mechanism. But when you're trying to detect or develop an electrochemical biosensor for microRNA, there are some, let's say, design criteria that you want to look into. So the talk today is going to be focusing on this little miniaturized biosensing surface. What is the engineering principles that we applied? What basically happens on this little miniaturized surface, and how did we design and engineer it? So some analytical, considerations to improve and to enhance your analytical performance for an electrochemical biosensor. This is typically what you want to have when you're choosing your materials. You want a material that's very, very conductive, such that your readout is going to be an electrochemical readout. You want your material, transduction material, to have very high conductivity properties. You want to have, of course, a very high signal, right? And one way to achieve that is to make sure that you have a lot of biorecognition sites on your material, such that all of the targets are captured. And of course, you want to have very high target specificity, right? You're not just detecting any random nucleic acid, you're detecting exactly the specific one that you're interested in. And what I'm going to talk about today is how we address all of these through the choice of materials, through the choice of sensing strategy, and through the choice of chemistry. So I'm going to introduce you to a material maybe nobody's. Has anybody heard of Maxines before? Please raise your hand if you're interested. Oh, one person. Wonderful. So this is going to be really exciting to introduce you to this particular material, Maxine. So it's going to be our transduction material. We will have PNA, of course, because I loved it in my PhD and I carried it on in my research group. And then we're using a chemistry that everybody loves here, but the copper-free one, copper-free quick chemistry to functionalize the bioreceptor onto the nanomaterial that is going to act as our transduction material. Okay, so so let me introduce you to Maxines. So when I first joined at House a year and a half ago, I joined the Material Science and Engineering program. And of course, as a very young assistant professor, I went around talking to much more senior faculty, asking them, what are you guys up to? Is there a material you can hand me over and I can try to make biosensors out of? And so as I was going along, I came across Professor Hussam Sharif, who actually develops something completely different. So he develops micro supercapacitors for energy harvesting and energy storage applications. And he uses Maxines to do that. And so the reason why is because Maxine has very high conductivity properties, electronic conductivity properties. And when you want to kind of transfer that energy to a current and move it from one material to another, there's no losses, there's no signal loss. So high current conductivity properties. The other really nice thing is that a very high specific surface area, like any 2D nanomaterial. The really interesting thing about it is that this 2D nanomaterial is covered with surface functional groups that are extremely hydrophilic. Okay, so when he told me that, I'm like, okay, tell me more. Maybe I could do something out of that. And so, what are they? What do they look like? So this is actually the precursor, the Max phase here, and they do interesting chemistries in their lab to etch out one of the phases through typically acidic etching. And then essentially what you get are these nanomaterials. They're very kind of thin, nanometric in the Z dimension, and then in the lateral dimensions, they're kind of microscopic in size. And essentially what it is, it's represented by this formula, right? M subscript n+1, xn, and then tx. Where M is a transition metal, right? It's any one of those. Typically, it's titanium. X is carbon or nitrogen, right here. And then T represents the surface functional group. And the surface functional group can be hydroxyl groups, oxygen, fluorine, and chlorine. So what you have here is essentially a metal carbide. And then on the surface of the metal carbide, you decorate it fully with surface functional groups that everybody knows how to functionalize, like hydroxyl groups, for example. And that makes them very, very stable, makes them very hydrophilic, and makes them really fun to functionalize and play with. And so what I was trying to take advantage of are these particular properties. Firstly, the high electrical conductivity. This is actually an order of magnitude higher than reduced graphene oxide. So very conductive, of course, very large specific surface area, but you also have these functional groups. Typically in any other 2D nanomaterial, 0.1 and 3, so A and C, are always in a trade-off. But in this material, it's not in a trade-off, which makes it just perfect for us for use in electrochemical biosensors, right? Of course, hydrophilic, which is wonderful. So that means I can be putting some aqueous media around that and aqueous solutions and working with something that we're typically used to working with. And they also remain very, very stable in solution over time, in water over time. So this is what you want to imagine when you're looking at this 3D nanomaterial. On the surface, everything red is these nice hydroxyl groups. And in the middle there, you have this carbide network where electrons can be transported very, very quickly, very easy. Wonderful. And so I decided, why not? Let me try to use it as a charge transfer promoter and use this material as my transduction material in an electrochemical biosensor. All right, so I went on and had a look at what's happening with the field of MaxEons. So you'll see that the field of MaxEons is growing exponentially since its discovery in 2011 by Professor Yuri Gogotsi. But then if you search for MaxEon and biosensors, it's a really, really new field. So 2018, great, there's not that much in it, but it's also growing exponentially. There's a lot of interest in the use of this material in bio applications. So you'll see here a couple of examples of where MaxEons have been applied, mainly other types of sensors, so gas sensors, strain sensors, and there's a little quadrant there for biosensors. If you look a bit more into it, people have applied MaxEons, let's say for glucose biosensing, and also this gliotoxin biosensing. But the main thing we notice is people are not really taking advantage of the MaxEon. What they're doing is they're creating MaxEon plus nanomaterial nanocomposite. So they're combining MaxEon with another nanomaterial, making a nanocomposite, and then physically immobilizing something like glucose oxidase enzyme or other bioreceptor inside, and then using that for electrochemical detection. So we identified 2 limitations, right? So the first one is graphene plus MaxEon nanocomposite, and then they immobilize an enzyme, a glucose oxidase. The second one, to achieve enough sensitivity, they're having to add an additional signal amplification steps by the use of HRP enzymes. So there's always either an enzyme or a nanocomposite material. And that we identify as a limitation that's increasing the complexity of their device. Limited, we've also noticed that there's limited robustness in these materials, and that the functionalization strategy is typically some type of physical adsorption between the bioreceptor, the oligo, or the antibody, and the material itself. There's also limited specificity in the choice of the materials. So, of course, for us, we're trying to detect microRNA, and of course, I'm going to choose PNA as my bioreceptor that's super robust, and Savannah already talked about all of the advantages of peptide nucleic acids as robust synthetic oligos. So, if nobody takes on PNAs, I will Savannah and do a lot of research with it, don't worry. So this is, the DNA backbone, and the PNA backbone has this pseudopeptide backbone. Of course, Watson-Crick base pairing can happen. And all these advantages are there because of the lack of electrostatic repulsion. So thermal stability, even under extreme conditions, specificity, of course, and you can automate the synthesis of it with solid phase peptide synthesis that is very well understood. So this is the setup that we have in the lab. We start with a synthesis of crude product. You can go up to tens of milligrams, 20, 30 milligrams with our automated peptide synthesizer. We then purify with HPLC. We do some mass spec to confirm that we've got the right oligo synthesized, and then we freeze dry it. Very, very quickly, the synthesis, how does it work? It's exactly the same as solid phase peptide synthesis, where you have a resin, and then you're adding monomers one by one through activation, coupling, and then deprotection of the big protecting group, FMOC. And then you repeat that cycle over and over again until you get your oligo. Unfortunately, with peptide nucleic acids, because of the lack of sugar, the phosphates, you have limited, at least it's very difficult to make very long PNAs because of the hydrophobicity. So there are ways around it by modifying the backbone, by adding arginines, and things like that. And so this is how we make our PNAs. What we really love doing in the lab is to rationally design PNAs for various applications. And this slide is here just to show you the versatility of PNA and how tunable it can be. So, of course, you can play with the sequence. Of course, actually, people have been playing with the backbone of this by adding some other group to improve the solubility and even improve the specificity of materials. You can add anchoring functionalities on one end, and then application-specific moieties on another end. And this enables you to bind and functionalize your PNA on whatever surface or material you like. Paper, we've done hydrogels, we've done nanomaterials, glass, of course, and then some electrodes, and that's what we're going to talk about today. With application-specific moieties, you can actually add, obviously, some materials that enable you to do electrochemical transduction, of course, dyes, and people are interested in therapeutic applications of this. People have already, and we have tried this, added some cell-penetrating peptides to one end that can carry the PNA into the cell very easily without any carrier, without lipofectamine or anything like that. That's not my field, but we like to collaborate in case people are interested. So, for today, we have our PNA here, and we added an anchoring functionality that enabled us to do very highly specific bioorthogonal click chemistry onto our MaxScenes, so something everybody loves. And this is the PNA that we made. Show you. So we started with a short PNA to start off easy, and same thing as what Savan showed. We put some arginines to help with our solubility, and you'll see on this side we have a striated alkyne. We've got the DBCO group right there to enable us to do copper-free click. Great, and so this enables us to do direct copper-free click onto the surface of MaxScene directly, right? This is never exploited. Typically, people try to add another nanomaterial, gold nanoparticles and things like that, but we really wanted to take advantage of this electron transport and make sure that PNA is directly on the nanomaterial of interest. All right, and so with this synthesized nanomaterial, I'll show you the chemistry of it, but with this nanomaterial, the whole idea is that we were able to do enzyme-free, application-free detection of microRNA. And how does it work? Essentially, what we do is we drop acid on a standard electrode, a GCE electrode, right? So you have your PNA there, and then we add our biological fluid sample. In our preliminary results, this is just 5 microliters of microRNA. And of course, in the presence of your target microRNA, you're going to get a specific hybridization there. This is typically 25 minutes at room temperature. And then, of course, you want to wash off any non-specifically bound nucleic acids. And we add a reporter. We add a reporter. So the nucleic acid itself is not redox active. We can't see it, but we added a reporter called methylene blue, very, very commonly used to detect the presence of duplexes. So the methylene blue will interpolate between the PNA microRNA duplex, and what we're actually detecting as our analytical signal is the oxidation reduction of this methylene blue, and this electron is actually mediated, or electron transport is mediated through the pi stack, through the duplex down to the electrode, and that's what we detect. So in the presence of microRNA, you see the red curve, you see an oxidation current or a peak current detected there. Without any microRNA or with non-specific microRNA, you don't see anything. You see kind of a flat curve as you're sweeping your voltage. You don't see any current there. So let's have a look at some of the chemistry. So this is what we're starting with. If you want to imagine something in your head, this is an SEM of the bare MaxScene. You'll see like this sheet-like structure. And the MaxScene that we worked with, which is the most commonly studied MaxScene, is a titanium carbide one. It's actually 3 layers of titanium with 2 layers of carbon. So titanium carbon sandwich almost structure. And then on the surface, there are many different functional groups, including a lot of hydroxyl. Great, hydroxyl is easy to work with. We can just silanize it. And so we bought this silane, like, aptase, instead of aptase with an amino head group, we bought an azido aptase, right, with an azide on the surface there. We see a change in morphology here nicely with SEM. This was done room temperature over 2 days. I don't know why it's 2 days. You can ask my postdoc, but it probably would work over like a couple of hours. I guess he was lazy. And then I don't know. But we'll see. I'll ask him to test less time. And then, of course, we have our PNA that already has the DBCO group. And so we did copper-free click there, room temperature overnight. Next morning, we've got this really nice strain-promoted alkyne enzyme cycloaddition, and you get the nice triazole formation there. And that's our final material. So with SEM, we could also, because I'm in the material science program, then of course we want to do all of the materials characterization. This is technically a completely new material hybrid that we created. So we looked at EDX, and really this is just showing, I know this is not a materials group, but this is just showing that we have the elements that we expect. You'll see some titanium element, so titanium peaks, carbon peaks, because that's the bare material, but you also see silicon here in blue. And you see nitrogen here showing that, yes, we've got the silanization reaction. And you can also look at the elemental mapping on EDX. You can see where these elements are popping up on the surface, and you'll see that we get a very nice homogeneous distribution of silicon everywhere, which is wonderful. This is what we want. Also, nitrogen is everywhere on the surface, very nicely homogeneously distributed. We did a lot more materials characterization. I'll show you a little bit more of what we've done. XPS is a really, really cool, also elemental composition materials characterization technique, where you can actually see all the elements, all the even bonds on the surfaces. So we did XPS to look at the bare maxine in red, post-salinization in black, post-click in blue. I don't want to spend too much time, but I'll just highlight a few cool things. So with the bare maxine, compared to the siliconized maxine, you see the appearance of silicon peaks. So great, we definitely have silicon on the surface. You also see appearance of nitrogen peaks. And if you zoom in on each of these peaks, you'll notice as an example of the characterization that we're doing. So if you look at the silicon 2p peak, this corresponds exactly to the binding energy of an SiO bond, which is wonderful. This is exactly what we expect to happen. And then if you zoom in on the nitrogen peak, that you'll also see that it is a specific binding energy for the azide group. So exactly at 400 electron volts and 405 electron volts. So this is just proving to us, yes, we've got all these functional groups on our surface. You can also do, XPS can actually be used for semi-quantitative analysis. So we should be able to work out the exact mole percentage of this PNA on the surface. Our preliminary results are telling us it's like 5 mole percent, but we're going to confirm that later on. We did Raman spec and also Zeta potential to comparing the bare and functionalized. We see very great significant differences as we expect. So I'm going to skip this and get to some of the electrochemical characterizations. So for electrochemical characterizations, what we did is we wanted to study each of the components individually. So starting with our bare electrode, right? We dip this electrode in a redox reporter, it's ruthenium, hexane. And we look at the oxidation reduction of this reporter with bare DT as the transducer material. And you can see a current here at 2.24, exactly where we expected for ruthenium. Great. Now, if we deposit, actually just drop cast our maxine onto the GCE, you do exactly the same experiment, you'll see in black this massive increase in current. So from 2 up to 100 microamps of current, which exactly tells us what we're expecting. There's a very, very high electronic conductivity properties of maxine, enabling electron transport through it. Now, in blue, what you see here is if the maxine was PNA functionalized. So we have PNA functionalized maxine also deposited on the surface, and of course you get reduction in current because now our maxine is actually covered with its surface with PNAs that are hindering this electron transport and hindering this redox reaction, which is what we expect as proof that it's definitely something functionalizing the surface, and we know from the previous results that it's definitely PNA. We confirmed these results with electrochemical impedance spectroscopy. Really here for the non-electric chemist, what you want to see is the electrochemical impedance spectroscopy basically tells us the charge transfer resistance at the electrode surface, right? And so how is that characterized? It's just the radius of these semicircles. So the greater the radius, the greater the charge transfer resistance. So you'll see something really fun here. If we have our bare glassy carbon electrode, the charge transfer resistance is about 1.8 kilo ohms. Now, if you put the maxine on the surface, look how far it goes. The charge transfer resistance goes down to 200 ohms. You're getting no resistance almost whatsoever. Electrons and electron transfer goes directly through to the electrodes. If there's PNA on the surface, it's going to hinder this electron transport, and you see the radius go back up. And now, if you hybridize the maxine onto if you hybridize the microRNA onto the PNA, now you have a much bulkier duplex, right? And that's going to hinder diffusion. Further, you see the radius go up. Good. So we know we have PNA. We know microRNA is maybe somehow hybridizing and blocking the surface. We really want to make sure that what we're seeing here is a specific interaction between PNA and microRNA. And so for the next experiments, what we're doing is we chose a specific, let's say, redox label that is specific towards the hybridization. So if there is duplex, then we should see this signal arising. And so for that, we chose to use methylene group, the most commonly used redox label. And you see this is nice heterocycle, and the nice thing about it is that it interacts with nucleic acids in various ways. It can interact with single-stranded nucleic acid just through a left-left interaction. And then for it interacts with double strands, so duplexes, with obviously interpolation, also some group binding can happen. So great, so we've chosen methylene blue as a reporter of this PNA microRNA hybridization. Of course, we want to do our controls. So we have just PNA on the surface, we incubate with methylene blue just 5 minutes, and then we wash off. So what we expect is the methylene blue is not going to interact with our PNA, and it's just going to wash off very easily off the surface, and we expect to see nothing, right? We expect to see no curve whatsoever, and that's shown in red. So we don't see any oxidation peak because there's nothing really redox active there. And then what happens, well, if we hybridize this or we add our target microRNA, it hybridizes to our PNA. We then add the methylene blue. It intercalates specifically due to the presence of a duplex. And then we run the same CB in TE buffer. The only redox active molecule is the methylene blue. It's only there because we have the duplex form. So you can see a really nice peak here that corresponds to the oxidation current or oxidation potential for methylene. Great. So now we know that this is happening. How can we enhance this signal? Right. So we're getting about 3 microamps of current in the presence of our microRNA. How can we really increase this? Because we obviously want to increase our sensitivity. So we know the only thing that's giving us signal is methylene blue. Can we increase the number of methylene blues per binding event? So instead of just having a few, we can have much more. And everything that I presented now is with this little 7-mer PNA. So easy, why don't we just increase the length of our PNA? By this time, we had optimized our solid phase peptide synthesis to be able to do longer PNA synthesis. Great. So we went up to 17-mer PNA. So it's exactly the same thing as I said, same functional group, but we have a much longer peptide nucleic acid. And so ideally, this means that based on the literature, methylene blue can interact, as I said, in many different ways. Spectroscopic analysis says that it's most commonly this intercalation effect. And so also some people are saying that it's around, let's say, 1 methylene blue per 2.4 base pairs. So our hope is if we're going from this 7-mer base pair duplex here towards 17-mer, we should at least see a times 2.4 increase in the signal because of the 2 times more methylene blues that can fit in between the duplexes. So hopefully we see that, and that's exactly what we saw. So this is a recalibration curve for the 7-mer in red, and we did exactly the same thing. So different concentrations of microRNA, but now with the 17-mer, and you can see this really nice increase in sensitivity quantified by this slope of the linear regression line. I don't know why I didn't draw it here, but if you fit a linear regression line, your slope comes out to 2 times greater, which is wonderful, and that also reduces our limit of detection. What we really found interesting here, if we kind of stop and think about it, is that there is no kind of methylene blue or no redox molecule in the solution where the electrode is deposited in. The only redox molecule, as I said, is methylene blue. And if we have this really long 17-mer duplex, then methylene blue is going to be intercalated throughout it. And most of my methylene blues are going to be quite far away from my electrode surface, right? So maybe like 3 nanometers to 6 nanometers away from my electrode surface. So the only way that we are detecting current, right, the only way that we're detecting actually electrons at the surface of this electrode and this redox reaction is if this electron transport is mediated through the duplex itself, right? And so this is really cool because a lot of previous research work has shown that this pi stack, right, in the duplexes can actually mediate very, very efficiently electron transport through it. And I think that's what we're seeing, which is really cool. So our next things is, can we increase the number of methylene blues? Can we change this kind of binding? And I guess this audience would be, much more, I guess it's something more similar to your expertise to look into and to think about. So this is it. So the final thing, of course, that we wanted to do is characterize the sensitivity and specificity. So as you can see here, you did cyclic whole timogram, same thing, but with different concentrations of microRNA. And you can see a calibration curve right here. So we can go to 180 attomolar, a bit worse than what Silvana presented, but still we're getting there. So 180 attomolar, which is wonderful for us without any amplification or enzymes being used. We, of course, looked at some specificity, right? So we designed some mutations in our target. So target 141, we have single nucleotide mutation 2 and 3. And you can see here very, very nicely that the highest one gave us about 25% signal, same as what Sylvain showed. And then as you increase the nucleotide mutations, you almost kill the signal to 0, which is really great. And finally, I'm going to go through the conclusions very quickly. This PNA MAXI9 hybrid is really cool. By the way, none of this is published. It's literally being written right now. So we're about to submit it soon once we have all the final results. Copperfleet Crick is great. It's bioorthogonal functionalization strategy, super robust. HiStack is really cool. And then we've got single nucleotide resolution. Biosensor is great. No amplification, no enzymes. But of course, so same as Sylvain, we really need to do multiplexing. We started with one, we need to multiplex, and we're going to use some different engineering principles to try to do that. We also want to miniaturize things. So rather than having this big, bulky glassy carbon electrode, we want to miniaturize it onto these screen printed electrodes for better portability. Of course, we want to validate at some point with clinical samples. None of this was clinical samples, just microRNA in low TE buffer. So hopefully we can maintain the performance. Of course, I want to thank you all for listening, and thank particular people who have definitely contributed and motivated a lot of this work. So of course, Sylvain, you just met and know very well, for introducing me to PNA and microRNA. Professor Hassan, who's the expert in the vaccine, who gave me the vaccines and contributed to that. My RS for the PNA synthesis, and postdoc for all the electrochemical biosensing. All of this is their work. And yeah, that's it. Thank you.